My name is Santiago Tabares, PhD student under supervision of Professor Morgan Mitchell, and I will be speaking about a certain challenge in near-infrared squeeze light generation, which is absorption effects. So, as part of the motivation, this is ICFO. We have here our group. We do optical pump magnetometers with rubidium vapor. We have some works on it. We also do Bose-Einstein condensates with rubidium. We also have this work. And for this reason, for us, it's natural to want a rubidium resonant squeezed light, more specifically with the D1 transition line that is 795 nanometers. The first squeezer that we built was done by Anna Predojevic. The results can be found here, in which she achieved 3 dBs of squeezing. And here I have an overview of the last generation of crystal-based squeezer at this wavelength. Ours is here. And as you can see, the maximum amount of squeezing that someone has ever achieved was this group, 5.6 dBs. And now we want to build a new light squeezer because ours was built nearly 20 years ago, and now we have more crystals, we have more powerful lasers. So we want to overcome this limit. So for the people that is not related to light squeezers, is quite simple. It's composed of more stages, but basically where the squeezing happens is here. You need this nonlinear crystal. You put it between in the middle of a cavity. Then you have an optical parametric oscillator. You pump it, and then you get what we call squeezed vacuum. Okay, so the natural question now is how to improve our squeezing. Well, the first approach that we took was, okay, let's take a look to this expression here that gives you the amount of squeezing that you can detect for these parameters. So you have the detector efficiency, you have a parameter called escape efficiency, your pump power that goes here, the oscillation threshold of the cavity, you have your sideband frequency and round trap cavity loss. And for the moment, I am going to restrict myself for low frequency scenario. That means that I am going to remove this term here because it's smaller than 1. Here I have plot of this expression as a function of this ratio and as a function of this escape efficiency for an efficiency of the detector of 85%. And okay, from here you can observe that the maximum amount of squeezing that we can get under these conditions is 8 dB, and you can achieve it for a power ratio of 1 here, and for escape efficiency of 1 as well. So we want to be near this region. Usually the escape efficiency is given by the material, by the cavity, and the thing that we can control is the power. So that's perfect. If we want a good amount of squeezing, the only thing that we need to do is to be close here, which means have a huge pump, right? Then if the pump increases, so here I put more and more light, then the squeezing must increase, right? So before I answer this question, I need to talk a bit more about this linear crystal, non-linear crystal that I have here. That is this effect, blue light induced infrared absorption, also known as BLIRA. It has been studied since the 90s. You can have here some papers. This specific plot was taken from this paper and is for a KTP crystal that is commonly used in squeezers. And it shows here the dependence of BLIRA against the intensity of the blue pump. And what this graph shows you is basically that if you have this crystal, right, and then you are shining it with blue light and red light, and then suddenly you increase your blue light power, what's going to happen with the red light is that it gets attenuated because the crystal starts to absorb it, right? So, is it bad? No. The correct answer is that it's really bad. Why? first we need to find a way to incorporate this into our model, right? So let me write down here more explicitly the power threshold and the escape efficiency. Uh, so here I have this transmission mirror that is a physical transmittance of a mirror that belongs to the cavity. You have this loss, is not a real mirror, it's a leaky mirror that is a very well-known model for intracavity losses. Here you have this G that is called a coupling constant. Somehow is like the gain of your process. So this is somehow like losses against gains. And for our model, we took the similar approach as with this. So we have this coefficient, this term called Erblira. So it's a reflectance of a leaky beam splitter that we introduce in our model that models a new loss. So, okay, I will put it here. This is our new loss. And which function follows this expression? Well, here first, I will assume that there is an intrinsic infrared absorption that is proper to the material. And then I will assume that there is some increase that first, let's assume that we don't know why it increases. And okay, we take this, we incorporate it into these expressions, and then in the squeezing function. And then we plot it. So here I have, again, pump power, infrared absorption. This is the delta alpha that I showed before. This simulation was run with these parameters. And again, as before, as expected, no, if you have a huge pump power here, you have this squeezing, and of course, if your infrared absorption that implies a loss increases, your system does it worse, right? But we know that we cannot we cannot be at arbitrary values of this plot, because what this article tells us is that we need to follow this curve because of Blira, right? So let me draw it. So again, here I have this mirror, this beam splitter, and then this curve that was drawn, taking into account this study. And basically what this shows is that if you wanted to be here with this power, now because of Blira you cannot be there. You need to move here because you need to follow this curve. I know that this is a little bit hard to see. That's why I have this other plot here. So this blue trace is this function evaluated for the Blira scenario, which will be this zero here, this horizontal line. And then this black trace is this function evaluated along this curve. So it's the Blira scenario. So if before you were here, if Blira didn't exist, you will be here. But because Blira exists, it moves here. That implies a 5 dB loss into your squeezer. And that's bad, no? And it also shows that you are limited, because now it doesn't matter if you have a strong pump, your optimum value of pump power goes here. And okay, so this answers my previous question. No, if you have a more powerful laser source, it doesn't necessarily improves your squeezer. Okay, so now we need to pay attention to the crystal. And now the next question is, what is this ultimate crystal? Well, here I have this comparison of different crystals. So KTP is very well known because if you take a look, it's the material with the higher gain and with the higher nonlinear coefficient, and this gain that, for example, appears here in the power threshold. Again, this is like a trade-off between losses and gains. If you take a look to this graph, you say, okay, KTP is awesome. Maybe it's the best material. Maybe if you put some rubidium in it, it maybe improves. But again, if you do this, you are ignoring the losses and you need to consider them. So now in this other study, you can observe they have this infrared absorption. And this loss, again, is proportional to the infrared absorption. So now, if you take a look to all the crystals that they measure, KTP is the worst, right? So maybe for this scenario, KTP is not the best option, although it has a higher gain, but it also implies higher blira. So now we need to take a look to a different crystal, LBGO, for example, or the stoichiometric lithium tantalate. We don't know. We need to study more. So, as a summary of my talk, I've shown that blira has a non-negligible effect uh, in squeezing. It negates the contribution of more powerful lasers, and therefore more focus need to be put into the material properties and some other properties as crystal length and beam focusing. A small advertisement before I finish. There are two colleagues here now, Thomas and Roman. They work with single atoms. He has a talk, he has a poster. I am sure that they will be very happy to share their information with you. So if you can visit him right now, it would be very nice. I would like to thank the contributors and thank you for your attention.
Thank you. Thank you for this comprehensive review of the interesting effect. Any questions, comments?
Yes.
Yes, please.
Very interesting. So, do you have any kind of feeling about which material can help us to
Any feeling about what?
about which material can kind of be like kind of have the trade-off between like
Okay, yeah. Which
lower
is the
gain?
ultimate material?
Yeah. Oh, yeah. Just
Not really, not really, because from this plot, you see, okay, rubidium has nice gain. Maybe rubidium doped KTP has a better gain, but from here, you see that it also exhibits more blira. The problem, for example, with this is, SLT, it has higher gain. I think it's 9 picometers per volt. But for our wavelength, you need to use third order quasi-phase matching, so it decreases the nonlinear coefficient by 3. So if, for example, if it was possible to periodically poll the SLT for this wavelength, it will be much better because it has less losses than KTP. But because of this problem, we don't know. We also we have this crystal that is new. It has a very low nonlinear coefficient, but maybe it also has very low gain. So very low losses. So maybe we don't really know, but maybe we care more about blira than in the gain itself.
Right, thank you.
Yes.
Hello, and very nice talk. Have you think to use BIBO crystal?
Which crystal?
BIBO.
L-
BIBO is not your list, but BIBO has almost the same nonlinear coefficients of
okay.
those crystals is quite transparent for UV region.
Yeah. Okay.
Maybe it's idea for you to check.
Okay. Okay. I think there are no studies of blira in this crystal, or
I'm not sure, but the LKB lab, Nicholas Trapp, he used this BIBO in SPOP cavities. So I think it's
okay.
quite nice.
Okay. Thank you.
Thank you. I would like to ask about hints on the physical mechanism of blira and whether you could do something with it, like, I don't know, saturate it, bleach it, or something like that.
Yes. Okay. So the mechanism behind blira is not very well understood. There is some model that was proposed in the 90s that implies a two-center charge transport model. But apart from that, there is no final model. And yes, from this graph, you see that maybe it saturates, at least for this regime. We don't really know because there are no further studies. This other, okay, the study that appears here, it doesn't show any saturation. So we don't really know. Also, there is another study
I
in
would think that
the.
you could like, for example, saturated with a incoherent infrared light shining from the back, such that you have like
No, we don't.
no,
No, because
probably not.
okay. So the problem with Blear is that it reacts. It appears when you have huge amount of blue light,
Sure.
right? So it's not related. It activates with blue light. So maybe it saturates, maybe it doesn't. I cannot give you a final answer.
I see. Yep, but interesting. Thanks.
Yes.
Let's move the last question to
Okay.
after the session.
Okay.
Tule.
Thank you for your talk. At which threads hold power do you come to work with?
Excuse me.
Which is the threshold power are you working with?
This the amount of power.
Yeah, the threshold power.
Power threshold.
Yeah.
Yes. Okay. For this simulation is 250 milliwatt. Well, yeah, it's
Okay. Thank you.
250 milliwatt in this case. But this value depends on, again, these parameters and on Blear as well. So your power threshold maybe is here, but again, as Blear increases, your power threshold also increases, so it becomes dependent on the blue power, which is also an impairment.
Thank you.
All right. Thank you.
Okay.